The next and final couple topics that we want to extend from single first order equations to systems of first order equations are properties about the continuity of solutions. So we have a theorem that states that for each t in the maximal interval of existence, or in a maximal interval of existence, the solution phi of xi, or phi of t, passing through a point xi naught, and really we'll just say passing through a point xi, is continuous as a function of xi. And again, I will be proving this theorem just like the previous main theorem on existence and uniqueness of solutions. This proof is in Kelly chapter 8. But and actually a more general result is proved there. However, it's just important for us to have these results so we can be confident when we're writing down our differential equations and modeling using these models that come from systems. We want to also extend the idea of orbits, and this has a nice definitive extension to systems. Say if xi of t is a solution, and the solution that we're talking about is to the initial value problem star. So if xi of t is a solution of star on a maximal interval of existence, for t from alpha to omega, then the set xi of t such that instead of points in phase space, xi of t such that t is in this maximal interval of existence is a subset of Rn, and it's called an orbit of the ODE. And the concept of orbit in the general phase space involves collecting, first solving for all of the critical points, and then collecting all of the solutions in a given in a given orbit that's separated between all of the intervals of existence, just like in the one-dimensional case. We also have a similar shifting theorem. and that's if xi of t satisfies the differential equation, the system, on some interval from C to D, so for t in such an interval, then for any constant h, function nu of t, which is defined as xi of t plus h, also satisfies the ODE star. This is on the new interval from C plus H to D plus H. Oh, and this should be shifted xi of t minus h. And furthermore, we can prove very, very nicely that if two orbits of the differential equation star have a common point, then the orbits are identical. So this is a theorem that I'll go through the proof of because it's relatively straightforward. So we'll assume that xi of t solves the differential equation on some interval from C to D, and to find nu of t to be the solution xi of t but shifted by h. For t in the interval from C plus h to D plus h. And if we differentiate eta, this is the same thing as differentiating eta 1 to eta n, which by definition of eta is the same thing as xi 1 prime of t minus h times 1 from the chain rule down to xi n prime of t minus h times 1, again times the chain rule. Which is the same thing as xi prime of t minus h times 1 but because xi prime satisfies the differential equation, this is the same thing as saying that eta prime of t is exactly equal to this function g of xi of t minus h, or g of eta. This is how we define eta of t. So there you have it. This is the proof of part 1. And the proof of part 2 of the theorem is a little bit more involved, but it uses the shifting theorem, the proof of part 1. So if we assume that xi1 of t and xi2 of t are solutions to the differential equation star, and we also assume that they have a common point, which means that at some point t1, xi1 of t is equal to xi2 of t, we can go through and directly show that these any two trajectories with a common point have to be equal. We can do this by introducing an auxiliary function. So we'll consider nu of t, which is defined as xi2 of t, but shifted by t1 and also shifted by t2. So minus t1 plus t2. Xi of t, or eta of t, satisfies the ODE. And this is directly because of the shifting theorem from before. We're just shifting this by a positive h, or a negative h, depending on what the value of t2 minus t1 is. And because of this, and the fact that if you consider what the value of eta of t1 is, eta of t1 is equal to xi2 of t1 minus t1 plus t2, or just xi2 of t2, which means that at this eta of t1, this is equal to the point xi2 of t2. And because of from the main existence uniqueness theorem, if we have a unique solution, then this means that this new shifted function, eta of t, has to be identical to x. Or sorry, not x, but xi1 of t. For all t in the maximal interval of existence, or for all t from alpha to t on this orbit. And this proves the theorem for us, because if this has to be true, this means then that xi2 of t minus t1 plus t2, which is just eta of t, has to be equal to xi1 of t for all t on the orbit from alpha to t to omega. And this exactly gives us what we want, because it's saying that really any two solutions on a maximal interval of existence, the same orbit, that cross one another are just related to one another and exactly the same as one another for all t. You just have to shift the possible parameterizations of the two solutions. So these two theorems are very, very powerful and will give us some very, very nice results when we go to argue and make certain arguments about some of the systems that we're going to encounter. And all of these results can be applied to the general population models that we've discussed so far, which are very nice. And the idea is that those are the first real examples that we'll see. In the next lecture, we'll see a number of different examples from mechanics and how to deal with certain problems from mechanics of motion. These new examples will show far and wide that this is the best way of going through and understanding a given system, is to develop the theory and then go through and apply it to applied problems. So I want to note here that the orbits of star partition the phase space Rn, which means that essentially these two theorems will allow us to conclude that each point of Rn lies on exactly one orbit. So let's get into some examples. I want to go through and show how to apply some of the theory we've talked about in the previous couple pages. And the best way to do that is by looking at some simple examples. So let's consider the differential equation xi, the system of differential equations where xi is xy and dxi dt, or xi dot for short, is equal to negative, or y negative x. So this is, the right hand side here is our function g of xi. This is a function of the two variables x and y, and this is a function of the two variables x and y. And not only that, this is an autonomous system of first order ODEs. Specifically that x dot is equal to y and y dot is equal to negative x. So the idea here is that very often when we go through to determine the trajectories in phase space to get the phase diagram, in this case the phase plane of the system, we can use various results from calculus. specifically from the implicit function theorem, we have this really nice result that the derivative of y with respect to x is going to be the same thing as the derivative of y with respect to t divided by the derivative of x with respect to t. Right, and this is assuming that these functions are nice enough and that the main thing here is that x dot is non-zero. So this then gives the equation, well, y dot is negative x and x dot is y. So this gives us a new differential equation that holds inside the phase plane. And this new differential equation is a separable differential equation that when we multiply both sides by y and then integrate, we get the antiderivative of y dy is equal to the antiderivative of negative x dx, which gives y squared over 2 is equal to negative x squared over 2 plus c, which is the same thing as the implicit equation x squared plus y squared is equal to 2 times c, or d for short. This is just an arbitrary constant of integration. By the way, before we even go through and solve this, we can classify the equilibrium points. This is going to have equilibrium points when y equals 0 and when negative x is equal to 0. So we have an equilibrium point at the origin. And then after the process of going through and solving for the actual shape of the phase curves, we see that these phase curves or orbits in phase space are going to take the form of circles that are all centered at this equilibrium point. And the circles have a radius of the square root of d, whatever that is, because this is what the level curves of this function look like. By the way, this solution method is the same solution method that you can go through and do to find the solution to the original log of Volterra system that we discussed earlier, which is very neat. But one of the things that we can point out is that this equilibrium point is going to be a stable equilibrium point, but not an asymptotically stable equilibrium point. And we can see that, and this is not going to be a direct proof of this, but it is going to be just kind of a picture showing why this is a stable equilibrium point. For any epsilon, no matter how small you choose to draw around this equilibrium point, there will always be a corresponding delta region or delta ball around this equilibrium point, such that for any initial condition in delta, the solution will stay within the epsilon ball. This is true for any size epsilon ball, no matter how small you want to go with the epsilon ball, because the orbits are always circles for this this equation. But it's not asymptotically stable because for none of these orbits, right, there exists no small enough interval or small enough delta ball that solutions inside of it converge to the equilibrium point. There is no such delta ball. This is just a quick explanation of why this equilibrium point is stable but not asymptotically stable. So the next example that we'll consider is actually a second order ordinary differential equation for x. So that x is equal to x minus x cubed. And right at the beginning, you can say, well, the theory that we just covered doesn't cover second order ODEs, and specifically this is a second order nonlinear ODE. So you can ask, well, what do we do? And the easiest thing to do is to rewrite this as a system of first order ODEs by defining y, a new variable y, as x prime for the derivative of x. We can rewrite this system of ODEs as x prime is equal to y, and because y is equal to x prime, x double prime is equal to y prime. So y prime is equal to x minus x cubed. And this is a system of two first order nonlinear ODEs, which is equivalent to the system that we or the single differential equation that we started with. This is also an autonomous system. So we can go through and apply the theory that we've just kind of constructed. Equilibrium points are where y equals 0 and where x times 1 minus x squared equals 0. And this can be satisfied in two ways. The first one is where x equals 0 or where x is equal to plus or minus 1. So to get an idea of what this phase space is going to look like, we have a two-dimensional space for our orbits. We're going to have three equilibrium points, one right here, and one right here. And one of the things that helps us out is to draw what are called the nullclines. For this system right here, the nullclines are the line x equals 0 and the line y equals 0. These intersect at the origin, which is the intersection of nullclines, are always the critical points. And you can see very clearly here that this nullcline corresponds to y prime equals 0. Is at any point for any trajectory on this nullcline, y is not changing. And same thing for this nullcline right here, x prime is equal to 0. So for any point on this nullcline, x is not changing. This might not be super well visualized here because of the fact that this is a freehand drawing and it's being drawn to scale. I really want to emphasize this. The rate of change of x here is 0 in this circle. Very, very hard to draw a circle freehand. But what's nice about these implicit curves is that you can directly visualize them using Desmos as well. So we'll see that when we get the form for this right here, this equation right here, we want to be able to visualize this using Desmos. But so we can visualize the null lines of this equation in a similar manner. We'll do when y equals 0, that corresponds to x prime equals 0. So the first main null line is this curve right here. This is x dot is equal to 0 for any point in this curve. And the second null line is going to correspond to all of the x values and y values for which the derivative of y is equal to 0. And that corresponds to these three curves right here. So one of the things about null lines is that you can always determine the direction of solution away from the null lines in the phase space. For the previous example, on the null lines, the various values of the derivative of the quantities are 0. However, as we move away from the null lines, you can always determine the sign of each of these values and put in, obtain exactly what direction the solution is traveling away from the null lines. So the solution curves for this solution are very interesting, and we're seeing that it's very kind of split up here. So you might not initially see what the solution curves are, but luckily this example can be solved just like we did before. So if we recall by the implicit function theorem, that dy dx is going to equal y dot over x dot, and x dot is non-zero. Then we get that this is going to be equal to x minus x cubed over y, which is again a separate differential equation for x and y. So we can go through and this is going to be then the integral of y dy, antiderivative of y dy is going to be the antiderivative of x minus x cubed dx, which gives us that y squared over 2 is equal to x squared over 2 minus x to the 4th over 4 plus some constant c. So we'll multiply by 2 to simplify this a little bit, but ultimately this becomes then the curve x to the 4th over 2 plus y squared minus x squared is equal to c, or 2 times c, where we'll call 2 times c d for short. So that the orbits of this system of differential equations in phase space are given by the level curves of this function. For various values of d, this is going to have various shapes. And the shapes are actually very, very interesting here. We actually have, so for the circle problem, the only valid value of d was positive or 0. 0 being the critical point or the equilibrium point, and then positive values of d being circles around the origin. However, for this example, negative values of d and positive values of d give us a solution. So the idea is that we have to be very, very careful here when we're plotting out the level curve of this function. So let's take a look at this in Desmos and try and get the desired result. So this is the Desmos plot, and I've included a plot of the null lines, specifically when y equals 0 and when x equals 0, 1, or minus 1. So we have the critical points here and the null lines. And then if we go through and plot that solution that we just found, x squared, or x to the 4th over 2 plus y squared minus x squared is equal to d. And we add a slider for d. You see that these curves for various values of d can be very interesting. When d is less than critical value here, we don't have any curves. But then when d is around negative 0.3, you have curves that look like this, up until the point where d is 0. This curve, by the way, when d equals 0, is sometimes called the separatrix, because it separates two distinct types of solutions or orbits from one another. So when d is, not too small, but small, less than 0, we have two separate orbits in our phase space. And when d goes to 0, and I'll make this range a little bit better, so we'll go from negative 0.3 to maybe positive 2 in steps of 0.001. So we can really see the clean distinction between the types of orbits. We can go a little bit lower than 0.3, maybe to 0.5. So you see that for negative values of d, you have orbits that look like this. Up until you hit d equals 0, which gives you this orbit right here. And then for larger values of d, so greater than 0, you get orbits that take on this shape right here. So if we draw out some of these orbits, we'll do negative 0.3, negative 0.4, negative 0.2, negative 0.1, 0, then 0.1, 0.2, 0.3, and 0.4. And I'll color all of the orbits where this is positive, solid blue, or solid red. I'll color the separatrix orbit of black, and then all of the negative values I'll dash the lines, or dot the lines, and color them blue. So you can better see this plot right here. But this is in the phase plane what the orbits of this system of differential equations look like. And they represent the solutions, right? These orbits represent the solutions of that first order, or that first single second order ODE, which is really cool. So what we're seeing here is that we have this separatrix curve. Oops. And it looks like this. And like this. This is my definitely not to scale freehand drawing. And then for any orbit inside this region, any initial condition inside this region, the orbit goes around this critical point, goes around this critical point, and then for any initial condition outside of the separatrix, you get a solution curve that takes this general peanut shape. And all of the solutions are essentially classified by this work that we've done, which is very, very cool. And so the last thing I want to talk about is that I mentioned is that this method that we've applied to this last example is typical of any higher order single ODE. So any single higher order ordinary differential equation can be rewritten as a system of first order ODEs, sometimes called the equivalent system. So suppose we have the first order ODE you have a very general first order ODE, or nth order ODE. And this takes the form of a general function of the form a multivariable function f of t y dot y double dot, where dot here again is just the derivative notation that we introduced before, and in general it can depend on all of the derivatives up to and including the nth derivative of our unknown function y. Is that equal to 0? This is the form that any nth order ODE will take. And just like in the last example, which is a second order ODE that we reduced to a system of first order ODEs, we can do that for any given general example. We define y naught, this is not critical point notation, this is just y naught, or y, this is a function of t, that y naught is equal to y1 is equal to y naught prime, it's the same thing as y prime, y2 is equal to y1 prime, and instead of the primes, I'll stick with the same notation, the dot notation that I'm using up here. So then y2 will define as y1 dot, which in reality is the second derivative of y. And we continue this procedure all the way up to yn minus 2 is defined to be equal to yn minus 3 dot, and I'll make a little bit more space over here. This is really just the n minus second derivative of y in disguise in a new notation. And we do this all the way up until yn minus 1, which is defined as being equal to yn minus 2 dot, or yn minus 2 prime, which is really just the n minus first derivative of y in disguise. And so this constitutes a system of n minus 1 equations. The first equation is for y dot, and this is saying that y naught prime is equal to y1. The second equation is for y double prime, and this is that y1 prime is equal to y2, and this continues all the way down to equation n minus 2, which is an equation really defining the n minus second derivative of y. This is the equation that y n minus 3 dot is equal to, let's make some room here because I want to really indicate why this is a system of n minus 1 equations. So y minus 3 dot is equal to yn minus 2 and then lastly our n minus first equation, which is for n minus first derivative of y, is saying that y n minus 2 is equal to yn minus 1. And so this is only n minus 1 equations, but the last equation here, or the nth equation that completes the system, is then just going to be that relationship between all of these variables, which is that f of t, comma y0, y1, y2, all the way up to yn minus 2, yn minus 1, and then lastly the nth derivative of y, which is yn minus 1 dot, is equal to 0. So this system of n first order differential equations is in general equivalent to the single nth order equation that we started with. And the only other possible caveat which sometimes occurs is if this function is a complicated function of this last derivative, which it very well may be, but very often we can express this in terms of the notation we had before, if we can solve for that last derivative as yn minus 1 dot in terms of everything else. Specifically, we'll say, let's say we can solve for yn minus 1 dot equal that, and it's equal to some function lowercase f of t, comma y naught y1 to yn minus 1. Then we attain a system of first order ODEs that is of the form that we talked about before. So where xi is y naught, y1, all the way up to yn minus 1. And then xi prime, the derivative is y naught prime, or y naught y1 prime, all the way to yn minus 1 prime. This will be equal to y1, y2, all the way up too, and I'll include some more of the end terms here so you really see what's going on. Y minus 2 prime is y minus 1. And then the last expression here is this function, lowercase f of t in all of the y's. So in general, this is equal to then some vector function g of y comma t. So our initial nth order differential equation, it can be rewritten as a system. This is a non-autonomous system if it depends on t. Of first order ODEs. And this is a very common technique that we'll use whenever we have an nth order ODE. But this will conclude today's lecture. Thank you very much for tuning in. I hope you have a great day and that you learned something.